NASA just discovered a black hole that weighs more than 100 billion suns. That's not a typo. 100 billion. It's so massive, it shouldn't exist according to every model we have. Yet, there it sits, 5.8 billion light years away, casually breaking the laws of physics we thought we understood. This thing is called Phoenix A, and it's rewriting what we know about the universe. If you want to see just how deep this rabbit hole goes, smash that like button and subscribe, because what we're about to uncover will change how you see reality itself. Let's dive in. To grasp what Phoenix A truly is, you need to forget almost everything you think you know about black holes. When most people hear the term black hole, they picture something from science fiction, maybe a swirling vortex in space that sucks in nearby spaceships, or perhaps the relatively modest supermassive black hole at the center of our own Milky Way galaxy, called Sagittarius A star. That one weighs about 4 million times the mass of our sun, and it's already so incomprehensibly massive that trying to visualize it makes your brain hurt. But Phoenix A makes Sagittarius A star look like a grain of sand next to Mount Everest. We're talking about a black hole that tips the cosmic scales at more than 100 billion solar masses. Let that sink in for a moment. 100 billion suns, not planets, not moons, but stars like the one that gives us life, each one containing 99.8% of all the mass in our entire solar system. And Phoenix A has swallowed the equivalent of 100 billion of them. The sheer scale is so extreme that astronomers had to invent a new category just to describe it. Most black holes at galaxy centers are called supermassive, a term that already sounds like hyperbole, but Phoenix A blows past that designation entirely and enters what scientists now call the ultramassive range. This isn't just semantics or scientists getting excited about labels. The jump from supermassive to ultramassive represents a fundamental shift in how these objects behave and what they mean for the structure of the universe itself. To understand why Phoenix A is so special, we need to talk about what a black hole actually is. And I mean really is, not the Hollywood version. At its core, a black hole is a region of space-time where gravity has become so intense that it warps the fabric of reality itself. Einstein showed us that massive objects bend space and time around them, like a bowling ball placed on a stretched rubber sheet. The heavier the object, the deeper the dent. A black hole is what happens when that dent becomes infinite, when the rubber sheet tears completely. At the center of every black hole sits something called a singularity, a point where all the mass gets compressed into a space so small it might as well be dimensionless. All those 100 billion suns worth of matter in Phoenix A, crushed down into a region smaller than an atom, maybe even smaller than the smallest particles we know of. The density there is so extreme that our physics equations literally break down and spit out infinity symbols. We can't describe what happens at the singularity because the math just stops working. But here's where it gets wild. That singularity is surrounded by an invisible boundary called the event horizon. And this is the point of no return. The event horizon isn't a physical surface you could touch. It's more like an invisible line in space, where the escape velocity equals the speed of light. Think about that for a second. To escape Earth's gravity, you need to travel at about 11 kilometers per second. To escape the sun's gravity from its surface, you'd need to go about 618 kilometers per second. But at the event horizon of a black hole, you'd need to travel at 299,792 kilometers per second, exact speed of light. And since nothing with mass can reach light speed, according to Einstein's relativity, nothing that crosses that boundary can ever come back out. Not matter, not energy, not even light itself. For Phoenix A, that event horizon is absolutely enormous. We're talking about a radius that stretches roughly 1,000 astronomical units. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So Phoenix A's event horizon extends 1,000 times that distance, which means if you place this monster where our sun sits. Its boundary of no escape would reach far beyond the orbit of Neptune, past Pluto, deep into the Kuiper Belt, where icy dwarf planets drift in the outer darkness. The entire solar system, as we know it, would fit inside Phoenix A's event horizon with room to spare. Everything we've ever sent into space, every planet we've discovered, every comet that's ever lit up our skies, all of it could vanish into Phoenix A and barely make a dent. Now here's something that messes with your intuition. Despite having the mass of 100 billion suns, Phoenix A isn't actually that dense when you average it out across its volume. This sounds crazy, but it's true. If you calculated the average density inside the event horizon, you'd find it's actually less dense than water, maybe even less dense than air, depending on exactly how massive it is. How is that possible when we just said the singularity is infinitely dense? It's because the event horizon is so incredibly huge. Volume increases with the cube of radius. So when you have a black hole this massive, the event horizon balloons out to such enormous distances that even 100 billion solar masses spread across that space becomes relatively diffuse. Of course, all that mass is actually concentrated at the singularity in the very center. The rest is just empty warped space-time, but mathematically, the average density drops. This means, and this is genuinely bizarre, that you could theoretically cross the event horizon of an ultramassive black hole like Phoenix A and not immediately notice anything wrong. There'd be no wall, no sudden jolt, no instant spaghettification. You'd just keep falling. And for a while, you might not even realize you'd crossed the point of no return. The tidal forces near the event horizon of such a massive black hole are actually quite gentle because the gravitational gradient is spread out over such a vast distance. It's only as you fell deeper, closer to the singularity, that the tidal forces would ramp up and eventually tear you apart atom by atom. But we're getting ahead of ourselves. The event horizon is just the boundary. The real action happens just outside it, in a region called the accretion disk. This is where Phoenix A does most of its feeding, and where it generates the unimaginable amounts of energy that make it visible across nearly 6 billion light-years of space. Matter doesn't fall straight into a black hole. Because of angular momentum and conservation of energy, it spirals inward, forming a massive disk of gas, dust, and plasma that rotates around the black hole at speeds approaching light speed. In Phoenix A's case, this disk is absolutely massive, potentially spanning thousands of light-years across, and it's hot. We're not talking about the heat of a summer day, or even the surface of the sun. The temperatures in the inner accretion disk reach billions of degrees, hot enough that atoms are completely stripped of their electrons, and the matter exists as a roiling plasma soup. At these temperatures, the disk doesn't just glow, it screams across the electromagnetic spectrum. It pumps out X-rays, gamma rays, ultraviolet radiation, visible light, infrared, radio waves, everything. The energy output is so intense that the accretion disk around Phoenix A can outshine entire galaxies. Think about that. A structure that's technically just the leftovers swirling around a black hole produces more light than hundreds of billions of stars combined. This is why we can detect Phoenix A from so far away. We're not seeing the black hole itself, which by definition emits no light. We're seeing the brilliant death spiral of matter as it gets consumed, the last desperate radiation emitted by gas and dust before it crosses the event horizon and vanishes forever. The process of accretion is also how Phoenix A grows. Every particle that crosses the event horizon adds to the black hole's mass, making it slightly heavier, slightly larger. And here's where the numbers start to get truly disturbing. Phoenix A is currently feeding at a rate that defies comprehension. Estimates suggest it's consuming matter at a rate of hundreds to potentially thousands of solar masses per year. That means every single year, Phoenix A swallows the equivalent of hundreds of stars. In just 1 million years, a blink of an eye in cosmic terms, It could theoretically add another 100 million solar masses to its bulk. The mechanics of how this feeding works are still not fully understood, but we know it involves a delicate balance of forces. As matter spirals inward and heats up, it begins to radiate energy. That radiation creates outward pressure, pushing against the infalling material. At a certain point, the radiation pressure becomes so intense that it should theoretically halt any further accretion. This is called the Eddington limit, named after astronomer Arthur Eddington, who first calculated it. For a black hole the size of Phoenix A, the Eddington limit suggests a maximum feeding rate, beyond which the radiation pressure would blow away any additional matter before it could fall in. And yet Phoenix A seems to be feeding at, or possibly even beyond, this theoretical limit. How, we're not entirely sure. Some models suggest the accretion disk might be clumpy and irregular, with dense filaments of gas that can punch through the radiation pressure and fall directly toward the event horizon. Others propose that Phoenix A might be feeding in brief, intense bursts rather than at a steady rate, allowing it to temporarily exceed the Eddington limit during feeding frenzies. There's also the possibility that our understanding of the Eddington limit itself is incomplete, that there are physical processes we haven't accounted for that allow ultramassive black holes to feed more efficiently than we thought possible. Whatever the mechanism, the result is clear. Phoenix A is a feeding monster, and it's growing at a pace that shouldn't be sustainable. But it's not just the feeding that makes Phoenix A extraordinary. It's what happens to the energy that doesn't fall in. Not all the matter in the accretion disk crosses the event horizon. Some of it gets caught up in the black hole's powerful magnetic fields, which thread through the disk and get twisted into tight spirals by the rotation of the infalling matter. These magnetic field lines act like cosmic rails, channeling some of the plasma away from the black hole and accelerating it to incredible speeds. The result is a pair of jets, twin beams of matter and energy that shoot out from the poles of the black hole at velocities approaching 99% the speed of light. These jets are among the most powerful phenomena in the entire universe. In Phoenix A's case, they extend for millions of light years, carving enormous cavities in the surrounding intergalactic medium. We can see these jets in radio wavelengths, blazing across space like cosmic searchlights. The energy contained in just one of these jets is staggering, equivalent to the total energy output of billions of suns sustained over millions of years. And here's the kicker. These jets aren't just expelling energy randomly. They're actively shaping the environment around Phoenix A, heating gas, preventing it from cooling and collapsing in some regions, while compressing it and triggering star formation in others. The black hole isn't just a passive consumer, it's an active architect of cosmic structure. To truly appreciate the scale of Phoenix A, let's bring it back to something more relatable. Imagine you could somehow shrink our entire solar system down to the size of a single grain of sand. At that scale, the Milky Way galaxy would be about the size of North America. Phoenix A, just the black hole itself, not counting its jets or accretion disk, would still be the size of a small city on that scaled-down map. And the sphere of influence, where its gravity dominates, would stretch across multiple states. Its gravity is so strong that it controls the motion of stars and gas across distances of hundreds of thousands of light years. Entire galaxies orbit around it like planets around a sun. When we look at Phoenix A through our most powerful telescopes, we're seeing it as it was 5.8 billion years ago, because that's how long its light has taken to reach us. Back then, Earth was just forming. The solar system was still a chaotic mess of colliding planesimals, and life was still billions of years away from crawling onto land. And even at that ancient epoch, Phoenix A was already a fully formed ultramassive giant dominating its corner of the universe. This raises one of the most profound questions in all of astrophysics, a question we'll explore deeper in the next section. How did something this massive form so quickly? The universe itself is only about 13.8 billion years old. Phoenix A's light has been traveling for 5.8 billion years, which means we're seeing it as it existed when the universe was roughly 8 billion years old. That might sound like a long time, but in cosmic terms, it's practically infancy. Standard black hole growth models predict that it should take much longer for a black hole to reach even 10 billion solar masses through normal accretion and mergers. Phoenix A is 10 times heavier than that. According to our best theories, it simply shouldn't exist yet, and that's exactly what makes it so important. Phoenix A isn't just a record-breaking curiosity. It's a fundamental challenge to our understanding of how black holes form and grow, how galaxies evolve, and how the large-scale structure of the universe came to be. It's a cosmic anomaly that's forcing scientists to rethink everything they thought they knew about the most extreme objects in existence. And that's why this discovery matters so much. Here's where Phoenix A stops being just impressively large and starts becoming genuinely weird, because this black hole is doing something that, according to our understanding of galaxy evolution, it absolutely should not be doing. The Phoenix cluster where this monster lives is one of the most prolific star-forming regions ever discovered, cranking out new stars at a rate of around 700 to 800 solar masses per year. To put that in perspective, our entire Milky Way galaxy produces roughly 1 to 2 new stars per year on average. The Phoenix cluster is birthing stars at a rate hundreds of times faster than our galaxy. And this is happening right in the shadow of one of the most powerful black holes in the universe. This shouldn't be possible. And to understand why, we need to talk about something called AGN feedback, which stands for Active Galactic Nucleus Feedback. And it's one of the most important concepts in modern astrophysics. The basic idea is this. When a supermassive black hole actively feeds on surrounding matter, it doesn't just grow quietly. It releases enormous amounts of energy through radiation and those powerful jets we talked about. This energy heats up the gas in and around the galaxy, preventing it from cooling down and collapsing into dense clouds where stars can form. It's like a cosmic thermostat. The black hole feeds, heats up its environment, stops the gas from cooling, which in turn limits star formation, and also limits how much new material can fall into the black hole itself. Eventually, the black hole's growth slows, the heating decreases, gas starts to cool again, and the cycle can repeat. This feedback mechanism is crucial for explaining why galaxies don't just keep growing forever. Without it, all the gas in a galaxy would cool and collapse into stars or fall into the central black hole within a few 100 million years, and we'd see a universe full of dead galaxies with no gas left. Instead, AGN feedback acts as a regulator, keeping galaxies in a state of balance where star formation proceeds at a measured pace over billions of years. Every major galaxy in the universe shows evidence of this feedback process. We see it in the Milky Way, in Andromeda, in massive elliptical galaxies across the cosmos. It's one of the fundamental principles that helps us understand galaxy evolution. Except Phoenix A is completely ignoring this rule. Despite hosting an ultramassive black hole that's actively feeding and pumping out more energy than billions of stars, the Phoenix cluster is in the middle of one of the most intense starbursts ever observed. The gas isn't being heated and dispersed. It's cooling and collapsing into new stars at a furious rate. The system has somehow broken the feedback loop that should be regulating it, and nobody can quite figure out how. The first clue that something unusual was happening came when astronomers measured the X-ray emission from the Phoenix cluster. X-rays tell us about hot gas, and in galaxy clusters, that gas typically exists at temperatures of tens of millions of degrees, heated by a combination of gravitational compression and energy from the central black hole. But in the Phoenix cluster, they found something unexpected. The X-ray observations revealed a complex structure of filaments and streams where gas was actually cooling down, dropping from tens of millions of degrees to just millions of degrees, and in some regions potentially cooling even further. This cooling gas was flowing inward toward the cluster center at rates of thousands of solar masses per year. Think of it like a cosmic waterfall, with rivers of gas cascading toward Phoenix A. This phenomenon is called a cooling flow, and while it's been theorized to exist in galaxy clusters, finding such a strong example was remarkable. But here's where it gets paradoxical. Normally, when gas cools and flows toward a galaxy cluster center, the central black hole should heat it back up through its jets and radiation, stopping the cooling flow in its tracks. This is AGN feedback in action. The black hole prevents its own food supply from reaching it by heating the very gas that's trying to fall in. It's a self-regulating system. But in the Phoenix cluster, something has gone wrong with this regulation. The cooling flow is so strong that it's overwhelming the feedback. Gas is cooling faster than Phoenix A can heat it back up. Why? That's the billion-dollar question. One possibility is sheer scale. Phoenix A is so massive and feeding so voraciously that it's generating more energy than any black hole we've studied before. Perhaps at these extreme scales, the feedback mechanisms work differently. The jets from Phoenix A are powerful enough to carve those massive cavities in the surrounding gas, cavities that span millions of light years and contain enough empty space to fit thousands of galaxies. These cavities represent an absolutely staggering amount of energy, the equivalent of billions of supernovae going off in coordinated blasts. And yet, despite all that energy being pumped into the environment, it's not stopping the cooling flow. Some researchers think the jets might actually be helping the star formation rather than hindering it. Here's how that could work. When those powerful jets slam into the surrounding gas, they create shock waves that compress the material. Normally, compression heats things up, but if the compression happens in just the right way, it can create dense filaments of gas that are able to cool more efficiently because they're shielded from the black hole's radiation by surrounding layers of hotter material. It's like the jets are sculpting the gas into configurations that allow pockets of it to cool and form stars, despite the overall heating. This would be a completely counterintuitive effect, where the very mechanism that's supposed to prevent star formation is actually enabling it through complex hydrodynamic interactions. Think of it like using a flamethrower to create ice cubes. It sounds impossible, but if the flames somehow compress and isolate pockets of material in just the right way, you might end up with localized cooling even in a generally heated environment. Another possibility is timing. Perhaps we're catching the Phoenix cluster at a special moment in its evolution, a brief phase where the cooling flow has temporarily gotten ahead of the feedback. Black holes don't feed at constant rates. They go through cycles of activity and quiescence. Maybe Phoenix A recently went through a quieter period where its energy output dropped, allowing gas to cool and start flowing inward. Now that the black hole is feeding again, it's trying to heat things back up, but there's a lag time. The gas that's currently forming stars might have started cooling hundreds of millions of years ago when Phoenix A was less active. By the time the black hole ramped up its energy output, the star formation process was already well underway and couldn't be stopped. In this scenario, the paradox would resolve itself over time. Eventually, Phoenix A's feedback would catch up and shut down the cooling flow, bringing the system back into balance. We just happened to be observing it during a transient phase of extreme activity. But there's a third, more radical possibility that some scientists are beginning to consider. What if our understanding of AGN feedback is incomplete? What if there are regimes of black hole activity where the standard feedback mechanisms break down or work in reverse? Phoenix A might be showing us that ultramassive black holes don't behave like scaled-up versions of their smaller cousins. Maybe when you cross some threshold of mass or accretion rate, the physics fundamentally changes. Perhaps the radiation pressure that normally blows gas away becomes less effective when the black hole is this massive, because the gravitational pull is so strong, it can hold on to material despite the outward pressure. Or maybe the magnetic field structures around ultramassive black holes are configured differently, channeling energy in ways that don't effectively heat the surrounding gas. We're in uncharted territory here. Most of our models for AGN feedback come from studying black holes in the millions to low billions of solar masses range. Phoenix A is 100 billion solar masses. That's not just a quantitative difference. It might represent a qualitative shift in behavior. To make things even more complex, the star formation in the Phoenix cluster isn't happening uniformly. It's concentrated in specific regions, forming a pattern that seems to trace the structure of the cooling flow. High-resolution observations show filaments of cool gas stretching toward the cluster center, and along these filaments, bright knots of star formation light up like beads on a string. These aren't just any stars either. Many of them are massive, hot, young stars that will burn through their fuel in just a few million years before exploding as supernovae. The rate of supernova explosions in the Phoenix cluster must be extraordinary, with dozens or even hundreds going off every year. Each supernova adds its own feedback to the mix, heating gas and creating shock waves. In most galaxies, this stellar feedback would work alongside AGN feedback to regulate star formation. But in Phoenix, even the combined feedback from the black hole and all these exploding stars isn't enough to shut down the starburst. The system is out of control, running at a pace that models say should be unsustainable. And yet it's sustaining itself, at least for now. There's also the question of fuel supply. For the Phoenix cluster to maintain star formation at this rate, it needs a constant supply of fresh gas. Where is all that gas coming from? Galaxy clusters are generally gas-rich environments. The space between galaxies isn't empty. It's filled with hot ionized gas called the intercluster medium, and clusters like Phoenix contain enormous amounts of it, potentially more mass and gas than in all the stars of all the galaxies combined. This gas is the reservoir that feeds both the star formation and the black hole. But for the gas to form stars, it needs to cool down from millions of degrees to just tens of degrees. And that should be a slow process in the presence of AGN heating. The fact that it's happening so rapidly suggests there's something enhancing the cooling, some mechanism we don't fully understand. One intriguing clue comes from the metallicity of the gas. Metals in astronomy means any element heavier than hydrogen and helium, and the gas in the Phoenix cluster shows elevated levels of metals, particularly in the cooling regions. These metals come from previous generations of stars that lived, died, and expelled their enriched material back into space. Metals are important because they're efficient radiators. They can cool gas more effectively than pure hydrogen and helium, so the presence of metals might be helping the cooling flow overcome the AGN heating. But this creates a chicken and egg problem. The metals come from star formation, but the star formation requires cooling, which is enhanced by the metals. It's a feedback loop in itself, but one that promotes rather than inhibits star formation. Maybe Phoenix is caught in a runaway process where previous star formation enriched the gas, making it easier to cool, which triggered more star formation, which added more metals, further enhancing cooling, and so on. If this is the case, the Phoenix cluster might represent an unstable mode of galaxy evolution, a phase that can't last long in cosmic terms, but is incredibly dramatic while it does. Some models suggest that systems like this might exhaust their gas supply within a few 100 million years, either by converting it all into stars, or by the cumulative feedback eventually becoming strong enough to heat and disperse what's left. After that, the cluster would settle into a more typical state, with low star formation and a more balanced feedback cycle. But for now, we're witnessing something exceptional, a cosmic moment where the normal rules are suspended, and the universe shows us what happens when the throttle gets stuck wide open. The paradox of Phoenix A isn't just an isolated curiosity. It has profound implications for our understanding of how the most massive structures in the universe form and evolve. Galaxy clusters like Phoenix are the largest gravitationally bound systems that exist. They're cosmic cities, containing hundreds or thousands of galaxies, enormous amounts of dark matter, and vast quantities of hot gas. How these clusters grow and how their central galaxies evolve depends critically on the balance between cooling and heating, between star formation and AGN feedback. If that balance can break down in the way it seems to have in Phoenix, then our models for cluster evolution might be missing important physics. We might need to account for these extreme starburst phases in our simulations, which would change our predictions for how clusters looked in the early universe and how they'll evolve in the future. There's also a connection to the broader question of how black holes and galaxies co-evolve. Observations have shown that the mass of a galaxy's central black hole is tightly correlated with properties of the galaxy itself, particularly the mass of its central bulge. This relationship suggests that black holes and galaxies grow together, regulating each other through feedback processes. But Phoenix challenges this picture. Here we have a black hole that's grown to truly extreme mass, and it's surrounded by intense star formation rather than the quenched gas-poor environment we'd expect from strong feedback. Either Phoenix A's host galaxy is also extraordinarily massive, maintaining the correlation, or the relationship breaks down at these extreme scales. Current observations suggest the host galaxy is indeed massive, but whether it's massive enough to maintain the expected correlation is still being debated. If the relationship holds, Phoenix teaches us that even the most extreme systems follow the same basic rules. If it breaks down, we need to rethink those rules entirely. What makes all of this even more fascinating is that Phoenix isn't alone. As our telescopes improve and surveys cover more of the sky, we're finding more systems that seem to break the feedback rules, more clusters with strong cooling flows and intense starbursts, more ultramassive black holes that shouldn't have had time to grow so large. Phoenix might be the most extreme example we know of, but it's starting to look like it's part of a population of systems that operate in a regime we didn't know existed. These discoveries are forcing a revolution in how we think about the most extreme environments in the universe, and Phoenix A sits right at the center of that revolution, simultaneously feeding and creating, destroying and building, breaking every rule while somehow keeping its cosmic ecosystem alive. The existence of Phoenix A poses what might be the most fundamental question in all of black hole astrophysics, and it's deceptively simple to state, but brutally difficult to answer. How did it get so big, so fast? To understand why this is such a profound problem, we need to walk through the standard story of how black holes grow, and then see where that story completely falls apart when we try to apply it to Phoenix A. In the beginning, and by beginning I mean the early universe, roughly 13 billion years ago, there were no black holes at all, at least not the kind we're talking about. The universe was filled with hydrogen and helium gas, left over from the Big Bang, and gravity was slowly pulling that gas together into clumps that would become the first stars. These weren't stars like our sun. They were monsters, potentially hundreds or even thousands of times more massive, burning incredibly hot and bright, but dying young, exhausting their nuclear fuel in just a few million years. When these first-generation stars died, many of them would have collapsed into black holes, but these would be stellar mass black holes, weighing perhaps 10 to 100 times the mass of the Sun. That's the standard starting point, the seed from which all supermassive and ultramassive black holes supposedly grow. From there, the black hole needs to gain weight, and there are two main ways this can happen. The first is accretion, which we've already discussed, where the black hole feeds on surrounding gas and dust. The second is mergers, where two black holes collide and combine into a single larger one. Both processes take time, and that's where the problem begins. Let's talk about accretion first, because this is where the speed limit shows up. When a black hole feeds, it doesn't just vacuum up everything around it indiscriminately. The process is limited by physics, specifically by something called the Eddington limit. that we touched on earlier. Here's how it works. As matter spirals into a black hole and heats up in the accretion disk, it radiates energy, lots of it. This radiation creates outward pressure that pushes against the infalling material. At a certain feeding rate, the outward radiation pressure exactly balances the inward gravitational pull, and any additional matter trying to fall in gets blown away before it can reach the event horizon. This maximum sustainable feeding rate is the Eddington limit, and it depends on the black hole's mass. For a black hole of a given mass, you can calculate the maximum rate at which it can grow through accretion without blowing away its own food supply. The math works out such that a black hole feeding at the Eddington limit will grow exponentially, doubling its mass roughly every 50 million years. That might sound pretty fast, and over billions of years, it can produce substantial growth. If you start with a 100 solar mass black hole and let it feed continuously at the Eddington limit for 1 billion years, it could grow to about 100 million solar masses. That's impressive. But here's the catch. Phoenix A weighs 100 billion solar masses, and we're seeing it as it was 8 billion years after the Big Bang. Even if a seed black hole formed within the first few 100 million years of the universe's existence and fed continuously at the Eddington limit for the entire 7 to 8 billion years available, it still couldn't reach Phoenix A's mass. The numbers simply don't work. You'd need the black hole to feed at many times the Eddington limit for most of cosmic history, and that's supposed to be physically impossible. The radiation pressure should prevent it, unless it isn't impossible. And this is where theorists start getting creative. Maybe under certain extreme conditions, black holes can exceed the Eddington limit. If the accretion disk is particularly thick or geometrically complex, radiation might get trapped or absorbed before it can create enough outward pressure to halt the infall. Some models propose super Eddington accretion, where black holes can temporarily feed at rates 10 or even 100 times the Eddington limit. If Phoenix A went through phases of super Eddington growth, especially early in its history when fuel was abundant, it might have been able to pack on mass much faster than standard models allow. But even this might not be enough, which brings us to the second growth mechanism, mergers. When two galaxies collide, their central black holes eventually sink to the center of the merged system and spiral toward each other, ultimately colliding and forming a single larger black hole. Each merger can double or triple the black hole's mass almost instantly, at least on cosmic timescales. And in the early universe, galaxy mergers were far more common than they are today. The universe was smaller, denser, and galaxies were packed more closely together, leading to frequent collisions. If Phoenix A's host galaxy went through a particularly violent history of mergers, absorbing dozens or hundreds of smaller galaxies over billions of years, the central black hole could have grown through a series of merger events. Each time a new galaxy was devoured, its black hole would add to Phoenix A's mass. String together enough mergers, and you might be able to build an ultramassive black hole. But there's a problem with this scenario too, and it's called the final parsec problem. When two black holes are orbiting each other, they lose energy by gravitationally interacting with nearby stars, flinging them away like cosmic slingshots. This causes the black holes to spiral closer together, but once they get within about 1 parsec of each other, which is roughly 3 light years, they run out of stars to interact with. The region around them has been cleared out by previous interactions, and without a way to lose more energy, the black holes can stall in their inspiral, orbiting each other indefinitely, without ever merging. Recent research suggests this problem might not be as severe as once thought. Gas in the system can provide additional drag, and gravitational wave radiation becomes important at very close separations, eventually forcing the merger. But it does slow things down, and it means you can't just assume that every galaxy merger leads to an immediate black hole merger. There are time delays involved, sometimes hundreds of millions of years, and that time adds up. If you factor in these delays, it becomes even harder to build something as massive as Phoenix A within the available time, so we're stuck. Normal accretion is too slow. Super Eddington accretion is theoretically difficult to maintain, and mergers have their own timing problems. How then does Phoenix A exist? This is where the really exotic ideas come in. Theories that push the boundaries of what we think is possible. One of the most intriguing is the direct collapse scenario, and it's radically different from the standard story. Instead of starting with a stellar mass black hole and growing it up, what if Phoenix A, or at least a much more massive seed that would become Phoenix A, formed all at once from the direct collapse of a massive gas cloud? In the very early universe, under special conditions, enormous clouds of primordial gas containing hundreds of thousands or even millions of solar masses could have collapsed directly into black holes without ever forming stars first. This would require unusual circumstances. Normally, when gas clouds collapse, they fragment into smaller pieces that become individual stars. But if the gas is kept unusually hot, or if the cloud is rotating in just the right way, or if there's intense radiation from nearby sources preventing normal star formation, the cloud might collapse as a single entity, forming what's called a direct collapse black hole. These objects could weigh anywhere from 10,000 to 1 million solar masses, right from birth, giving them a huge head start compared to stellar mass seeds. If Phoenix A started as a direct collapse black hole, weighing say 1 million solar masses, and then grew through a combination of accretion and mergers, reaching 100 billion solar masses, becomes much more feasible within 8 billion years. You've shaved several doublings off the problem, and that might be just enough to make the math work. But direct collapse, black holes are still theoretical. We've never observed one forming, and we're not even entirely sure the conditions required for them to form actually existed in the early universe. Some simulations suggest they could have been relatively common, while others indicate they'd be extremely rare, maybe only a handful forming in the entire observable universe. If Phoenix A required a direct collapse origin, and if those events are as rare as some models suggest, then Phoenix A might be one of a kind, a cosmic fluke that we're incredibly lucky to have found. There's another possibility that sounds like science fiction, but is taken seriously by some researchers, and it involves primordial black holes. These are hypothetical black holes that could have formed in the very first moments after the Big Bang, not from collapsing stars, but from density fluctuations in the incredibly hot, dense plasma that filled the infant universe. If conditions were just right, regions that were slightly denser than average could have collapsed into black holes within the first second of cosmic history. Primordial black holes could have any mass, from microscopic to millions of solar masses, depending on the size of the density fluctuation that created them. If massive primordial black holes formed and survived to seed the first galaxies, they could provide the starting point for ultramassive black holes like Phoenix A. This would neatly solve the timing problem, because primordial black holes would already exist at the very beginning of cosmic structure formation, ready to start growing as soon as gas became available. But like direct collapse black holes, primordial black holes remain hypothetical. We have no definitive evidence they exist, and many models of the early universe suggest they should be extremely rare if they exist at all. Then there's the possibility that Phoenix A isn't a single black hole at all, at least not originally. What if it's the result of not just 2 or 3 mergers, but hundreds of them, a cascade of collisions that assembled an ultramassive black hole from dozens of smaller supermassive ones? In this scenario, Phoenix A's host galaxy would have been at the center of an unusually dense region of the early universe, a place where galaxies were packed together so tightly that mergers happened constantly. Over billions of years, the host galaxy would have cannibalized everything around it, accumulating mass and black holes like a cosmic vacuum cleaner. Each absorbed galaxy contributed its central black hole to the growing monster, and the final result is Phoenix A. This hierarchical merger scenario is attractive because we know galaxy mergers happen. We see them throughout cosmic history, and we know that galaxy clusters form through the gradual accumulation and merging of smaller structures. If Phoenix A sits in an unusually dense environment, which the Phoenix cluster certainly is, then it might have had access to more merger partners than typical galaxies. The problem with this explanation is scale. To build a 100 billion solar mass black hole through mergers alone, you'd need to combine hundreds of billion solar mass black holes, or thousands of 100 million solar mass ones. That's a lot of galaxies to destroy. And we should see evidence of that violent history in the structure of Phoenix A's host galaxy and the surrounding cluster. Some evidence does exist. The Phoenix cluster shows signs of past disturbances, and the central galaxy has a complex structure suggesting multiple merger events. But whether that's enough to account for Phoenix A's full mass is still unclear. There's also a more unsettling possibility that some physicists are beginning to explore, and it's that our fundamental understanding of gravity might need modification at these extreme scales. What if general relativity, Einstein's theory that describes gravity and has passed every test we've thrown at it for over a century, breaks down or behaves differently in the vicinity of ultramassive black holes? What if there are additional forces or effects that become important at these scales that we haven't accounted for? Some theories of quantum gravity predict modifications to black hole physics, particularly near the event horizon or in the strong field regime. Others suggest that black holes might not be perfect, one-way traps, but could leak information or energy in ways we don't currently understand. If any of these exotic effects are real, they could change the growth rate calculations and make it easier for ultramassive black holes to form. But these are speculative ideas, far from the mainstream, and most physicists are hesitant to invoke new physics when the old physics might still work if we just apply it more carefully. Another angle that researchers are exploring is environmental effects. Maybe Phoenix A grew so large because it happened to form in an exceptionally gas-rich region of the universe. The early universe wasn't uniform. Some regions had higher densities of matter than others, and those regions would have had more fuel available for black hole growth. If Phoenix A's birthplace was an overdensity, a pocket of space with significantly more gas than average, it might have had access to a much larger reservoir of material to consume. Combined with favorable dynamics, maybe strong gas flows funneling material toward the center. This could boost the accretion rate beyond what we'd expect in a typical environment. We're also learning that black hole growth might be more episodic than we thought. Instead of feeding steadily over billions of years, black holes might go through brief periods of extremely rapid growth, followed by long dormant phases. During an active phase, a black hole might feed at super Eddington rates for a few million years, bulking up significantly before feedback kicks in and shuts down the accretion. Then the system goes quiet for tens or hundreds of millions of years before another burst of activity begins. If Phoenix A went through many such cycles, with each burst adding a significant chunk of mass, the cumulative effect over billions of years could produce the ultramassive monster we see today. The challenge with all these scenarios is that we're trying to reconstruct billions of years of history from a single snapshot. We see Phoenix A as it is now, or rather as it was 8 billion years ago when its light began its journey to us. We don't know what it looked like earlier, or how its growth rate has changed over time. To really solve the formation mystery, we need more data. We need to find other ultramassive black holes at various stages of development and map out the full population. We need better simulations that can track black hole growth through realistic merger histories and accretion episodes. And we need deeper observations of Phoenix A itself to understand its current feeding rate, its host galaxy structure, and the history encoded in the surrounding cluster. Some of those observations are already underway. The James Webb Space Telescope is capable of peering back to earlier cosmic epochs and finding black holes in the process of forming. Radio telescope arrays are mapping the structure of jets and gas flows around systems like Phoenix A in unprecedented detail. Gravitational wave detectors are beginning to catch the merger events of smaller black holes, giving us insights into how these processes work. Each piece of data narrows down the possibilities and helps us understand which formation scenarios are viable and which can be ruled out. What we're learning is that Phoenix A probably didn't form through any single mechanism, but through a combination of favorable factors. Maybe it started as a relatively massive seed, either from direct collapse or from an unusually massive first-generation star. Maybe it formed in an overdense region with abundant fuel. Maybe it went through phases of super-Eddington accretion during the universe's gas-rich youth. Maybe it benefited from numerous mergers in a particularly violent environment. And maybe, just maybe, there's some physics we're still missing that allowed it to grow even faster than our current models predict. The truth is probably some messy combination of all these factors, and that messiness is actually reassuring in a way. It suggests that Phoenix A, while extreme, formed through natural processes, just pushed to their limits. It's not evidence of exotic physics or cosmic anomalies. It's evidence that the universe can create things at the very edge of what the laws of physics allow. And when we find those edge cases, they teach us where our understanding is incomplete. Phoenix A is a challenge, a puzzle, a cosmic Rosetta Stone that's forcing us to decode the language of black hole formation and growth. And the fact that it exists at all, despite all the reasons it shouldn't, tells us something profound. The universe is more creative, more extreme, and more capable of surprise than we ever imagined. And our theories, no matter how carefully constructed, always lag behind reality, scrambling to catch up with what nature has already built. Phoenix A isn't just sitting passively at the center of its cluster like some cosmic ornament. It's actively sculpting the universe around it, carving structure into space on scales so vast they defy comprehension. And what we're learning is that black holes like Phoenix A might not be mere consequences of galaxy formation, but rather the architects of it, the master builders that determine how galaxies grow, where stars form, and how the large-scale structure of the universe takes shape. To see this architecture in action, we need to zoom out and look at what Phoenix A has done to its neighborhood. And by neighborhood, I mean a region of space millions of light-years across. The most visible evidence of Phoenix A's influence comes from those radio jets we mentioned earlier, twin beams of plasma and electromagnetic radiation shooting out from the black hole's poles at nearly the speed of light. These jets aren't thin pencil beams. They're enormous structures, potentially hundreds of thousands of light-years wide and extending for millions of light-years in each direction. When these jets slam into the intergalactic medium, the hot, thin gas that fills the space between galaxies, they push it aside like a cosmic snowplow, creating enormous bubbles or cavities in the gas. Radio observations of the Phoenix cluster reveal two such cavities, one on each side of the central galaxy, and they're absolutely colossal. Each cavity is large enough to contain multiple galaxy clusters, representing a volume of space that's been effectively evacuated of gas by the mechanical energy of the jets. The amount of energy required to create these structures is mind-boggling, somewhere in the range of 10 to the 60 ergs, which is more energy than our sun will produce over its entire 10 billion-year lifetime, except released in a concentrated blast over just a few million years. These aren't gentle processes. They're violent, explosive events that reshape the cosmic landscape. But here's what makes this truly fascinating. These cavities aren't just empty voids. They're playing an active role in the physics of the cluster. The hot gas in the intergalactic medium wants to cool down and fall toward the center of the cluster where Phoenix A sits, pulled by gravity. As we discussed earlier, this should create a cooling flow that feeds both the black hole and star formation. But the cavities created by the jets act as obstacles to that flow, disrupting it and heating the gas through a process called PDV work, which is physics speak for the work done when you expand a gas against pressure. As the cavities expand, they push against the surrounding gas, compressing it and heating it up. This heat injection counteracts the cooling, at least in some regions, creating a complex pattern of hot and cool gas distributed throughout the cluster. If you could see the Phoenix cluster in X-ray vision, which is essentially what X-ray telescopes give us, you wouldn't see a smooth, uniform glow. You'd see an intricate structure of bright filaments, where gas is cooling and flowing inward, interspersed with darker regions where the gas has been heated or displaced by the jets. It looks less like a simple sphere and more like a cosmic spider web, with threads of different temperatures and densities weaving through each other in complex patterns. The jets are also magnetized, carrying powerful magnetic fields from the vicinity of the black hole out into intergalactic space. These fields thread through the gas and can channel its motion, creating preferential pathways for cooling flows and star formation. In some regions, the magnetic fields might actually help gas cool by organizing it into dense filaments that can radiate away their heat more efficiently. In other regions, they might stir up turbulence that prevents gas from settling into the dense configurations needed for star formation. The interplay between jets, magnetic fields, hot gas cooling flows, and star formation creates a phenomenally complex ecosystem, and Phoenix A sits at the center of it all, like a conductor leading a cosmic orchestra. What makes this even more remarkable is that we're not just seeing the current state of affairs, we're seeing a history written in the structure of the gas. Those cavities we talked about didn't form instantaneously. They grew over millions of years as the jets pushed outward. And they're not the only cavities either. Careful analysis of the X-ray images reveals hints of older, larger cavities further out from the cluster center, ghostly remnants of previous episodes of jet activity. This tells us that Phoenix A doesn't produce jets continuously, but rather in bursts, episodic explosions of energy that recur every few tens of millions of years. Each burst creates a new pair of cavities that expand outward, eventually stalling and fading as they lose energy to the surrounding gas. Meanwhile, closer to the black hole, conditions change and a new burst begins, starting the cycle over. The pattern of nested cavities at different distances from the cluster center is like tree rings, each one recording a moment in Phoenix A's history. By measuring the sizes and properties of these cavities, astronomers can reconstruct the black hole's activity over the past 100 million years or so, creating a timeline of when it was actively feeding and when it was relatively quiet. This episodic behavior is actually crucial for understanding how AGN feedback works. If Phoenix A were blasting out jets continuously at full power all the time, it would heat the cluster gas so much that nothing could cool and fall inward, and eventually the black hole would starve itself, running out of fuel. But by pulsing on and off, it creates a more sustainable balance. During the active phases, the jets heat gas and blow cavities, suppressing cooling flows. But during the quiet phases, the gas starts to cool again and flow back toward the center, replenishing the black hole's food supply and triggering a new burst of activity. It's a self-regulating cycle, a cosmic thermostat that keeps the system hovering around a balance point between too much cooling and too much heating. Except in Phoenix's case, the thermostat seems to be broken, or at least miscalibrated, because despite all this feedback, the cooling and star formation are still running at extreme levels. The architecture Phoenix A has created extends beyond just gas dynamics. It's also affected the distribution of galaxies in the cluster. When you map out where galaxies are located in the Phoenix cluster, you find they're not randomly scattered. They show a pattern of organization, with higher concentrations in certain regions and voids in others. Some of this structure is due to the overall gravitational potential of the cluster, massive concentrations of dark matter that pull galaxies into their neighborhoods. But some of it appears to be influenced by the jets and gas flows driven by Phoenix A. Galaxies tend to avoid the cavities created by the jets, which makes sense because those regions have been cleared of gas and aren't hospitable places for galaxies to exist. Instead, galaxies concentrate along the filaments of cooling gas, following the pathways laid down by the black hole's influence. In a very real sense, Phoenix A is determining where new galaxies can form and where existing ones can thrive. The jets are also accelerating particles to incredible energies, creating cosmic rays that permeate the cluster. These high-energy particles carry energy away from the black hole and deposit it throughout the cluster volume, contributing to the overall heating. They also generate radio emission as they spiral through magnetic fields, which is how we detect the jets in the first place. Radio telescopes tuned to specific frequencies can map out the structure of these jets in exquisite detail, revealing features like knots, where the jet brightens, bends where it's deflected by clumps of denser gas, and termination shocks where the jet slams into the surrounding medium and abruptly decelerates. Each of these features tells us something about the physics happening in and around the jet. One particularly interesting aspect of Phoenix A's architecture is how it affects the metallicity of gas throughout the cluster. Stars produce heavy elements through nuclear fusion in their cores, and when they die, particularly in supernova explosions, they scatter those elements into space. Over cosmic time, this metal-enriched gas mixes with the pristine hydrogen and helium that dominated the early universe, gradually increasing the overall metallicity. In galaxy clusters, the central galaxy usually has the highest metallicity because it's been forming stars the longest and has accumulated metals from all the smaller galaxies it's absorbed. But Phoenix A's jets are changing this pattern. By stirring and mixing gas throughout the cluster, they're spreading metal-enriched material from the central regions outward, creating a more uniform metallicity profile than we'd otherwise expect. At the same time, the intense star formation happening near the cluster center is pumping out fresh metals at an extraordinary rate, and supernovae from those stars are injecting that material into the gas with explosive force. The combined effect of jets and supernovae creates a complex circulation pattern where gas is constantly being churned, heated, cooled, enriched, and redistributed. It's like a cosmic weather system with Phoenix A as the low-pressure center driving everything. And just like Earth's weather creates climate zones and ecosystems, this cosmic weather creates regions with different properties that affect how galaxies evolve. Some areas are hot and turbulent, hostile to star formation, while others are cool and calm, perfect nurseries for new stars. The architecture extends even further when you consider the role of dark matter. Galaxy clusters like Phoenix are dominated by dark matter, the mysterious invisible substance that makes up most of the universe's mass. Dark matter doesn't emit light and doesn't interact with normal matter except through gravity, but its gravitational pull is what holds the cluster together and determines its overall structure. Phoenix A sits at the bottom of the cluster's gravitational potential well, the deepest point in the dark matter distribution, where gravity is strongest. Everything in the cluster, gas, galaxies, even light itself, feels the pull toward this center, and Phoenix A has grown so massive in part because it's located at this privileged position where material naturally accumulates. But the relationship goes both ways. As Phoenix A grew and began influencing its environment through feedback, it affected how gas and galaxies moved through the cluster, which in turn affected how the dark matter distribution evolved. Dark matter and normal matter are coupled through gravity, so large-scale motions in one affect the other. The jets from Phoenix A, by displacing vast quantities of gas, have subtly altered the gravitational field of the cluster, creating small perturbations in the dark matter distribution. These effects are tiny on an individual basis, but can accumulate over billions of years to produce measurable differences in cluster structure. Simulations of galaxy cluster formation that include AGN feedback produce clusters that look more like what we actually observe than simulations that leave it out, which tells us that black holes like Phoenix A are playing a crucial and non-negotiable role in shaping cosmic structure. There's also evidence that Phoenix A might be affecting the cluster on scales even larger than we can currently observe. Galaxy clusters don't exist in isolation. They're connected to other clusters and groups through filaments of matter called the cosmic web. These filaments are like cosmic highways along which gas flows from less dense regions toward denser ones, feeding the growth of clusters. Phoenix A's jets, if they're powerful enough, might be reaching beyond the cluster itself and affecting gas in these filaments, potentially altering the rate at which new material flows into the Phoenix cluster. Some theoretical models suggest that the most powerful jets from ultramassive black holes could extend for tens of millions of light years, reaching across the space between clusters and influencing structure formation on truly cosmic scales. We don't yet have the observational capability to confirm this for Phoenix A specifically, but future telescopes might be able to trace the jets to greater distances and see if this is really happening. If it is, it would mean that Phoenix A's influence isn't limited to its own cluster, but extends across a significant fraction of the observable universe, at least the neighborhood of space within a few tens of millions of light years. The architectural role of supermassive and ultramassive black holes has fundamentally changed how we think about galaxy formation. A few decades ago, black holes were thought to be interesting, but ultimately peripheral objects, end products of stellar evolution, or accidents of nature that happen to lurk at galaxy centers but didn't play a major role in how galaxies developed. Now we understand they're absolutely central to the story, possibly even the main characters. The mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's central bulge and with the velocity dispersion of stars in the galaxy, relationships that suggest a deep connection between black hole growth and galaxy growth. The leading explanation for these correlations is that black holes regulate galaxy formation through feedback. When a black hole feeds and releases energy, it heats gas and prevents it from cooling and forming stars, which limits how large the galaxy can grow. Conversely, when a galaxy undergoes a merger or captures new gas, some of that material feeds the black hole, causing it to grow in proportion to the galaxy. The two grow together in a dance of mutual influence, and the end result is the tight correlations we observe. Phoenix A represents this process taken to an extreme. It's not just regulating its galaxy, it's regulating an entire cluster, shaping the properties of dozens or hundreds of galaxies through its feedback. The fact that such regulation is possible tells us that the influence of black holes can extend far beyond individual galaxies to encompass the largest gravitationally bound structures in the universe. This has profound implications for cosmology, because it means you can't understand how the universe evolved without accounting for black holes. They're not optional extras or minor details, they're fundamental drivers of cosmic evolution, and any complete theory of how galaxies and clusters form must include them. The architecture Phoenix A has created is also temporary, in cosmic terms. Those cavities will eventually fade as the hot gas around them cools and flows back in, filling the voids. The jets will turn off or redirect as the black hole's accretion disk changes configuration, or as the fuel supply dwindles. The intense starburst will exhaust the available gas within a few 100 million years, and the cluster will settle into a quieter state. Future astronomers, observing the Phoenix cluster billions of years from now, might see only faint echoes of the activity we're witnessing today, ghostly remnants in the gas distribution, and an unusually massive black hole at the center, sleeping after its feast. But for now, we're catching Phoenix A in the act of creation, watching in real time as a black hole builds and shapes the universe around it. And that's an extraordinary privilege, a front row seat to one of the most powerful ongoing processes in the cosmos, where destruction and creation are two sides of the same coin, and where the darkest object in the universe is paradoxically responsible for lighting up one of the brightest. When we look at Phoenix A through our telescopes, we're not seeing it as it exists today in this moment. We're seeing it as it was 5.8 billion years ago, frozen in time, like a photograph from an era when the universe itself was fundamentally different from what it is now. The light that left Phoenix A back then has been traveling through expanding space for longer than Earth has existed as a solid planet, longer than our Sun has been a stable main sequence star, longer than the solar system has had its current configuration. That light began its journey when the universe was only 8 billion years old, barely half its current age of 13.8 billion years. And in that younger cosmos, things worked differently. The universe was denser, more compact, with galaxies packed closer together and collisions happening more frequently. The rate of star formation across the entire universe was higher, with more gas available to collapse into new suns. The cosmic web of large-scale structure was still actively forming, with filaments and clusters still in the process of assembling from smaller pieces. Phoenix A exists for us in that earlier epoch, a window into how the universe looked and behaved when it was young and wild, still settling into the patterns we see today. This time delay isn't just a curiosity, it's one of the most powerful tools we have for studying cosmic evolution, because every time we look at a distant object, we're literally looking back in time, seeing the universe at an earlier stage of development. Astronomers call this look-back time, and it's directly related to distance. The further away something is, the longer its light has taken to reach us, and the further back in time we're seeing. Phoenix A, at 5.8 billion light-years, gives us a look-back time of 5.8 billion years, which means we're observing an era roughly corresponding to when Earth's continents were just beginning to form their current shapes, when multicellular life was still confined to the oceans, when the first simple plants were beginning to colonize land. But in cosmic terms, this was still relatively recent history. The universe by that point had already gone through its period of rapid early evolution, had already formed most of its first generation of stars and galaxies, had already assembled galaxy clusters like Phoenix. What makes this look-back time particularly valuable for Phoenix A is that it shows us an ultramassive black hole already in place and actively feeding when the universe was only 8 billion years old. This is a crucial data point for understanding black hole formation timelines, because it tells us that whatever process created Phoenix A had to happen relatively quickly in cosmic terms. Within the first few billion years after the Big Bang, the light we're receiving encodes information about conditions in that earlier era. And by studying it carefully, we can reconstruct what the Phoenix cluster was like back then. Spectroscopy allows us to break the light down into its component wavelengths and look for the signatures of different elements and physical processes. We can measure the temperature of gas in the cluster by looking at X-ray emission lines, determine how fast material is moving by measuring Doppler shifts, and calculate the rate of star formation by detecting ultraviolet and infrared radiation from young stars. Each wavelength of light tells a different part of the story, and by combining observations across the electromagnetic spectrum, we build up a detailed picture of Phoenix A's environment 5.8 billion years ago. What that picture reveals is a system already in a state of extreme activity, not a young black hole just beginning its growth, but a mature monster that had already accumulated most of its mass and was feeding voraciously while simultaneously triggering intense star formation. This suggests that the most dramatic phase of Phoenix A's growth probably happened even earlier, perhaps when the universe was only a few billion years old, which makes the formation problem we discussed earlier even more acute. The look-back time also reveals something profound about the evolution of galaxy clusters. When we compare Phoenix to other clusters at different distances, and therefore different look-back times, we can trace how cluster properties change over cosmic history. Nearby clusters that we see as they are today tend to be more relaxed and evolved, with relatively low star formation rates, and black holes that are mostly dormant or feeding at modest rates. But as we look further back in time to higher redshift clusters, we find more systems like Phoenix that are actively forming stars and feeding their central black holes. This tells us that galaxy clusters go through an evolutionary sequence, starting as violent, gas-rich environments with high star formation and black hole activity, then gradually settling down over billions of years as they exhaust their gas supply and feedback processes quench further growth. Phoenix A represents a snapshot of this evolutionary sequence, captured at a relatively early stage when things were still dynamic and changing rapidly. The fact that Phoenix A was already so massive 5.8 billion years ago also has implications for the even earlier universe, the first few billion years after the Big Bang that we can barely observe directly. If Phoenix A had 100 billion solar masses by the time the universe was 8 billion years old, it must have had a substantial seed mass much earlier, perhaps within the first billion years of cosmic history. This connects to observations of very distant quasars, extremely bright active galactic nuclei, powered by supermassive black holes that have been found at redshifts corresponding to when the universe was less than 1 billion years old. Some of these early quasars have black holes weighing billions of solar masses, which is itself a major puzzle, because there's been even less time for growth. Phoenix A might be the descendant of one of these early quasars, a black hole that formed from a massive seed in the very early universe, and continued growing over billions of years to reach its current, ultramassive state. By studying systems like Phoenix at various look-back times, we can start to connect the dots between the earliest black holes and the ultramassive ones we see in the more recent universe, tracing the growth history across cosmic time. Another fascinating aspect of look-back time is that it allows us to study the properties of gas and stars in the earlier universe. The gas in the Phoenix cluster 5.8 billion years ago had a different composition than gas today. It was less enriched with heavy elements because fewer generations of stars had lived and died to produce those elements. By measuring the metallicity of gas in Phoenix and comparing it to nearby clusters, we can track how the chemical composition of the universe has changed over time, how successive generations of stars have gradually increased the abundance of carbon, oxygen, iron, and other elements that are essential for planet formation and potentially for life. The star formation happening in Phoenix also gives us insights into how stars formed in the earlier universe. The intense starburst we observe suggests that star formation in younger galaxy clusters could proceed at much higher rates than we see locally, creating massive star clusters and potentially affecting the kinds of stars that form. In environments with very high star formation rates, the gas might get compressed to higher densities, favoring the formation of more massive stars. These massive stars burn hot and die young, enriching the gas with metals and exploding as supernovae at a furious rate. The cumulative effect of thousands of supernovae going off over a few million years could fundamentally alter the cluster environment, driving powerful winds that expel gas and potentially even shutting down star formation in certain regions. Phoenix A shows us this process in action, a cosmic laboratory where we can study star formation under extreme conditions that no longer exist in the nearby universe. The look-back time also has a more philosophical dimension because it confronts us with the finite speed of light and the vastness of cosmic distances. The Phoenix A we see no longer exists in that form. By now, in the present moment, wherever that might be in Phoenix A's reference frame, another 5.8 billion years have passed. Stars that were just forming when the light left have long since died. The black hole has consumed additional material and grown larger. The cluster itself has continued to evolve, perhaps merging with other nearby clusters, perhaps exhausting its gas supply and falling quiet. We'll never know what Phoenix A looks like right now, because the information about its current state won't reach us for another 5.8 billion years. And by the time that light arrives, Earth might not exist anymore, the sun having expanded into a red giant and swallowed the inner planets. We're separated from Phoenix A, not just by distance, but by an unbridgeable gap in time, observing an event that's already ancient history, but that appears to us as it unfolds. This temporal displacement is true for everything we observe in the universe, beyond our immediate neighborhood, and it means that astronomy is fundamentally a historical science. We can never see the universe as it is now, only as it was. The night sky is a museum of the past, with each star and galaxy an exhibit from a different era. Some of the stars we see are relatively nearby, just a few light years away, so we're seeing them as they were a few years ago, essentially their present state. But other objects are millions or billions of light years distant, showing us the universe as it existed in completely different epochs. The most distant objects we can detect, galaxies at the edge of the observable universe, show us light that's been traveling for over 13 billion years, giving us a glimpse of the universe when it was just a few 100 million years old, in its infancy. Phoenix A sits somewhere in the middle of this cosmic timeline, far enough away to show us a substantially younger universe, but close enough that we can study it in detail with current telescopes. This makes it an ideal target for understanding how black holes and galaxy clusters evolved during a crucial period of cosmic history, when the universe was transitioning from its wild youth to the more settled middle age we see today. The 5.8 billion year look-back time also means that when the light we're receiving left Phoenix A, life on Earth was undergoing crucial evolutionary developments. Complex multicellular organisms were becoming established. The Cambrian explosion that gave rise to most modern animal body plans was already in the past, and life was beginning to colonize land. In a very real sense, Phoenix A's light has been traveling toward us for the entire span of complex life on Earth. Every species that's ever existed, every evolutionary innovation, from eyes to wings to brains, happened while Phoenix A's photons were in transit. This creates a strange connection across cosmic distances, a shared timeline, even though we and Phoenix A are causally disconnected and always will be. One of the challenges of studying objects with significant look-back time is accounting for the expansion of the universe. During the 5.8 billion years that Phoenix A's light has been traveling, space itself has been expanding, stretching the fabric of the cosmos and increasing distances between objects. This expansion has several effects on the light we receive. First, it redshifts the light, stretching its wavelength and shifting it toward the red end of the spectrum. The amount of redshift tells us how far away an object is and how long ago the light was emitted. For Phoenix A, the redshift corresponds to that 5.8 billion year travel time. Second, the expansion dilutes the light, spreading the photons across a larger and larger sphere as the universe grows. By the time Phoenix A's light reaches us, it's been diluted by a factor that depends on the expansion history of the universe over those 5.8 billion years. This is why distant objects appear so faint and why we need powerful telescopes to detect them. Third, the expansion affects the energy of individual photons, not just their wavelength, but their actual energy content, which is related to wavelength by quantum mechanics. Red-shifted light carries less energy than it did when it was emitted, which means we're receiving a dimmer, cooler version of Phoenix A's radiation than what was actually produced. All these effects must be carefully accounted for when we analyze observations using our understanding of cosmology and the expansion history encoded in the universe's geometry and composition. The look-back time provided by Phoenix A also allows us to test cosmological models. The fact that we can see Phoenix A at all, that its light successfully traversed 5.8 billion light-years of expanding space to reach us, confirms that the universe has remained transparent to light over that entire span of time. If there had been intervening clouds of dust or gas, or if the universe's expansion had behaved differently than predicted by our models, the light would have been absorbed or distorted in ways we could detect. The agreement between what we observe and what our models predict gives us confidence that we understand the large-scale behavior of the cosmos over the past several billion years. Moreover, by studying many objects at different look-back times, we can map out how various properties of the universe have changed over time, from the star formation rate to the abundance of different elements to the clustering of galaxies. Phoenix A is one data point in this larger survey, but an important one because it represents an extreme example that tests the limits of our models. When we observe Phoenix A, we're also seeing the effects of cosmic evolution on the light itself during its journey. The photons we receive have passed through intergalactic space, encountering regions of ionized gas, weak magnetic fields, and the subtle gravitational influence of dark matter structures along the way. Each interaction leaves a faint imprint that we can sometimes detect if we're clever enough. For instance, the light from Phoenix A has passed through numerous filaments of the cosmic web, and each filament contains hot ionized gas that absorbs specific wavelengths corresponding to spectral lines of elements like hydrogen and helium. By analyzing these absorption features, astronomers can map out the distribution of gas between us and Phoenix A, effectively using the black hole as a cosmic backlight to illuminate the otherwise invisible structure of the intergalactic medium. This technique has revealed that the space between galaxies isn't truly empty, but contains a vast network of gas filaments at various temperatures and densities, the raw material from which galaxies continue to grow. The journey of light from Phoenix A to Earth is itself an epic voyage, spanning more than a third of the universe's current age, and thinking about that journey helps us appreciate the sheer scale of what we're observing. A photon emitted from the accretion disk around Phoenix, 5.8 billion years ago, began by fighting its way through the intense radiation and magnetic fields near the black hole, scattering off electrons in the hot plasma, until it finally escaped into the relative calm of intergalactic space. From there, it traveled outward through the Phoenix cluster, passing by hundreds of galaxies, threading between them without interacting, because space is so vast and galaxies so sparse that collisions are incredibly unlikely. It crossed the boundary of the cluster and entered the darker regions between clusters, still moving at light speed as space expanded around it. Over billions of years, it passed through countless cosmic structures, always moving outward, always redshifting as the universe grew. Finally, after an unimaginable journey, it entered our local group of galaxies, passed through the Milky Way's outer halo, descended through the galactic disk, entered the solar system, traveled the last 8 light minutes from interstellar space to Earth's atmosphere, and struck a detector on one of our telescopes. Its journey complete. That single photon carried information across billions of light years and billions of years of time, and we caught it, decoded its message, and used it to learn about one of the most extreme objects in the universe. Multiply that story by trillions of photons, all arriving from slightly different parts of Phoenix A's accretion disk and jets, all carrying slightly different information, and you begin to understand how we can build up such detailed pictures of distant objects, despite never being able to visit them. Every observation of Phoenix A is an act of time travel, a glimpse into cosmic history, a connection to an era when the universe was younger and stranger, and a reminder that the past isn't gone, it's still out there, encoded in light that's been traveling through space for eons, waiting for someone to catch it and read its story. For all that we've learned about Phoenix A, for all the observations we've made, and the theories we've constructed, the uncomfortable truth is that we still don't understand it. Not really, not in the deep fundamental way that would allow us to predict its behavior or explain its existence from first principles. Phoenix A sits at the intersection of multiple unsolved problems in physics and astronomy, each one representing a gap in our knowledge that we're still struggling to fill. Let's start with the most profound mystery, one that applies not just to Phoenix A, but to every black hole in the universe. And that's the question of what happens at the singularity. According to general relativity, all the mass of a black hole collapses down to a point of infinite density at the center, a singularity where space-time curvature becomes infinite, and the equations we use to describe physics simply break down and give nonsensical answers. Physicists hate infinities because they usually signal that a theory has reached its limits and needs to be replaced by something more complete. Most scientists believe the singularity is telling us that general relativity, as successful as it's been, isn't the final word on gravity, that there's a deeper theory waiting to be discovered that describes what really happens at the center of a black hole. This theory would need to combine general relativity with quantum mechanics, creating what's called a theory of quantum gravity. And despite decades of effort by some of the brightest minds in physics, we still don't have a complete working version of such a theory. String theory is one candidate, loop quantum gravity is another, and there are various other approaches being explored, but none have been definitively confirmed or proven superior to the others. Without quantum gravity, we can't say what's really at the heart of Phoenix A. Maybe it's not a true singularity, but some kind of quantum object with enormous but finite density. Maybe information about the matter that falls in is somehow encoded in the structure of this object. Maybe there are connections to other universes or regions of space-time through what some theories call wormholes or Einstein-Rosen bridges. These ideas range from speculative to extremely speculative, but the point is that we genuinely don't know, and Phoenix A, with its 100 billion solar masses concentrated in an unknowable state, at its core, represents one of the largest repositories of this mystery in the observable universe. Then there's the information paradox, one of the most famous unsolved problems in theoretical physics. When something falls into a black hole, it carries information with it, information about its quantum state, its composition, its history. According to classical general relativity, that information is lost forever once it crosses the event horizon, trapped inside, and eventually consumed by the singularity. But this creates a problem because quantum mechanics says information can't be destroyed, it can only be transformed or relocated. The laws of quantum mechanics are time reversible, meaning that if you know the complete quantum state of a system at one moment, you can in principle calculate its state at any other moment, past or future. But if black holes destroy information, this reversibility is broken, which would mean quantum mechanics is wrong, or at least incomplete. Stephen Hawking discovered that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, radiation that we now call Hawking radiation. Over incredibly long timescales, this radiation would cause a black hole to evaporate completely, eventually disappearing in a final burst of energy. But here's the problem. Hawking radiation, as originally calculated, appears to be completely thermal, meaning it carries no information about what fell into the black hole. It's like random static, with no signal encoded in it. So when the black hole evaporates, the information about everything that fell in seems to vanish from the universe, violating the principles of quantum mechanics. This is the information paradox, and despite decades of work, we still don't have a consensus solution. Some physicists think the information is somehow encoded in the Hawking radiation in subtle correlations we haven't figured out how to detect. Others propose that information is stored on the event horizon itself in what's called a holographic principle, where the three-dimensional contents of the black hole are encoded as two-dimensional information on its surface. Still others suggest that black holes don't completely evaporate, but leave behind remnants that preserve the information, or that information escapes through connections to other universes, or that our notion of information itself needs to be revised. For Phoenix A, specifically, the information paradox is particularly acute because of the sheer amount of material it's consumed. Every star, every gas cloud, every particle that's fallen into Phoenix A over billions of years carried information. And if black holes truly destroy information, then Phoenix A represents one of the largest information erasure events in cosmic history, an ongoing deletion of data from the universe that violates our understanding of how quantum reality should work. We also don't understand how Phoenix A spins, and this is more than just a missing detail. It's actually crucial for understanding how the black hole behaves and how it affects its environment. Black holes can rotate, and when they do, they drag space-time around with them in an effect called frame dragging. The faster a black hole spins, the more it drags space-time, and at maximum spin the effects become extreme, with the region near the event horizon twisted into a spiral structure. The spin of a black hole affects where its innermost stable orbit is, which determines how close matter can orbit before plunging in. And this in turn affects the efficiency of accretion and the amount of energy that can be extracted. A rapidly spinning black hole can be more efficient at converting mass into energy potentially explaining why some active galactic nuclei are so luminous. The spin also affects the jets, with some models suggesting that jet power is directly related to how fast the black hole is spinning, energy being extracted from the rotational energy of the black hole itself through magnetic field interactions. For Phoenix A, we don't have a direct measurement of its spin. Measuring black hole spin is technically challenging, requiring detailed observations of X-ray emission from the innermost accretion disk, where relativistic effects are strongest. For a black hole as distant as Phoenix A, these observations are at the limit of current technology. We can make educated guesses, based on theoretical models, of how black holes accumulate spin through accretion and mergers, but without direct measurements, we're essentially guessing. If Phoenix A is spinning rapidly, it might help explain its powerful jets and high accretion rate. If it's spinning slowly, perhaps because its growth was dominated by chaotic mergers that canceled out angular momentum, then we'd need different explanations for its behavior. The spin question connects to broader uncertainties about Phoenix A's growth history, which we discussed earlier, but bears repeating in the context of what we don't know. We have theories about how ultramassive black holes could form, from direct collapse to runaway mergers to super Eddington accretion, but we don't know which path Phoenix A actually took because we can't observe its history directly. We're trying to reconstruct billions of years of evolution from a single snapshot, which is like trying to figure out a person's entire life story from one photograph. Some clues might be hidden in the properties of Phoenix A's host galaxy or in the structure of the surrounding cluster, but interpreting those clues requires assumptions about how galaxies and black holes co-evolve, and those assumptions themselves are based on models that might not be complete. There's also the question of whether Phoenix A is still growing, or if it's reached some kind of maximum mass. Is there an upper limit to how massive a black hole can become? Some theories suggest there might be, based on how feedback processes scale with mass, or on limits imposed by the finite amount of matter available in a galaxy cluster. But we don't know where that limit is, or even if it exists, and Phoenix A with its 100 billion solar masses might be approaching it, or might still have room to grow. The future evolution of Phoenix A is also uncertain and depends on factors we don't fully understand. We know it will eventually run out of easily accessible fuel as the star formation in the Phoenix cluster slows and the gas supply is exhausted or dispersed by feedback. But how long will that take? What will Phoenix A do after it stops feeding? Will it enter a dormant state, waiting for the next galaxy merger to deliver fresh material? Will it continue emitting weak jets, or go completely quiet? And on the longest timescales, what happens when Hawking radiation becomes important? Phoenix A is so massive that its Hawking radiation is incredibly faint, far weaker than the cosmic microwave background radiation that pervades the universe. It would take an unimaginably long time for Phoenix A to evaporate through Hawking radiation, far longer than the current age of the universe, so long that we're talking about timescales that make billions of years seem like an instant. Current estimates suggest a black hole of Phoenix A's mass would take something like 10 to the 100 years to evaporate completely, a 1 followed by 100 zeros, a number so large it's essentially meaningless in any practical sense. But in principle, given enough time, Phoenix A will shrink, slowly radiating away its mass until it finally vanishes. Except we don't even know if this is true, because we've never observed Hawking radiation directly. It's a theoretical prediction that hasn't been experimentally confirmed. There's another layer of mystery in how Phoenix A interacts with dark matter, the invisible substance that makes up most of the matter in the universe. We know dark matter exists because of its gravitational effects. We can see how it bends light through gravitational lensing and how it affects the motion of galaxies and the structure of galaxy clusters. The Phoenix cluster contains vast amounts of dark matter, probably 10 to 20 times more dark matter than normal matter, and Phoenix A sits at the center of this dark matter distribution. But how does dark matter interact with black holes? Does dark matter fall into black holes the same way normal matter does? if dark matter particles have very low interaction rates with normal matter. As most theories suggest, they might pass through the accretion disk without being slowed down or captured, only being consumed if they happen to pass directly through the event horizon. Or maybe dark matter does interact more strongly near black holes where densities and gravitational fields are extreme. Some exotic theories propose that black holes could be surrounded by halos of dark matter that affect their growth and behavior in ways we haven't accounted for. Phoenix A might be accreting dark matter along with normal matter, adding to its mass in ways we can't directly observe because dark matter doesn't emit light. If this is happening, our estimates of Phoenix A's mass based on its gravitational effects might be accurate, but our understanding of how it grew and how it's feeding could be missing a significant component. There's also uncertainty about the detailed structure of Phoenix A's accretion disk. We know matter is spiraling into the black hole and heating up, producing the radiation we observe, but the exact geometry and physics of the disk are still debated. Is it a thin disk where matter orbits in a plane, gradually spiraling inward through viscous friction? Or is it a thick disk where the material has significant vertical extent and turbulent motion? Does the disk extend all the way down to the innermost stable orbit, or is there a gap? How does the magnetic field thread through the disk, and how does it affect the accretion flow? Different models predict different observational signatures, but for a distant object like Phoenix A, we can't resolve the disk structure directly. We can only observe its integrated emission and try to infer the geometry from that. Even with our most powerful X-ray telescopes, Phoenix A's accretion disk is just a point source. We can't see its shape or measure its temperature profile directly. We can use spectroscopy to look for telltale features like iron emission lines that are broadened and shifted by relativistic effects near the black hole. And from those features, we can infer some properties of the inner disk. But there's still significant uncertainty, and different models can often fit the same data equally well. The jets from Phoenix A are another area where we have more questions than answers. We can observe the jets in radio wavelengths and map their structure, but we don't fully understand how they're launched or what determines their power. The leading model involves magnetic fields that get twisted by the rotating accretion disk and the spinning black hole, creating a magnetic pressure that launches material outward at relativistic speeds. But the details are complex and not fully worked out. How does the jet stay collimated over millions of light years instead of spreading out? What's the composition of the jet? Is it mostly electrons and positrons? Or does it contain significant amounts of protons and heavier particles? How much energy does the jet carry? And how is that energy distributed between kinetic energy of the moving particles, magnetic field energy, and radiation? These questions affect how we model the jet's impact on the surrounding environment and how we interpret observations of jets in other systems. For Phoenix A specifically, we see the large-scale structure of the jets and the cavities they've created, but we don't have observations of the jet base, where it's launched from the immediate vicinity of the black hole. That region is too small and too obscured by surrounding material for us to observe directly. So we're missing crucial information about the jet's origin. There's also the question of whether the jets are steady or variable. Do they operate continuously with a constant power output, or do they pulse and flicker on short timescales? Some observations of other black holes suggest jet activity can be highly variable, changing on timescales of hours to years. But for Phoenix A, we can only observe changes that happen over millions of years due to the light travel time. So any short-term variability is completely invisible to us. We're essentially watching a movie of Phoenix A in extreme slow motion, seeing only the averaged behavior over long timescales, and missing all the fast dynamics that might be crucial for understanding how the system works. Another fundamental unknown is what fraction of Phoenix A's mass is actually within the event horizon versus in the accretion disk and jets. When we quote Phoenix A's mass as 100 billion solar masses, we're typically referring to the total mass of the black hole itself, the mass that's already crossed the event horizon and been added to the singularity. But at any given moment, there's also significant mass in the accretion disk that's in the process of falling in, but hasn't crossed the horizon yet, and some mass in the jets that's being ejected and will never fall in. Depending on the accretion rate and the efficiency of jet launching, the accretion disk might contain anywhere from thousands to billions of solar masses of material that's orbiting the black hole but hasn't been consumed yet. This distinction matters because the accretion disk contributes to the total gravitational field we observe and affects the dynamics of surrounding objects, but it's not permanently part of the black hole and could in principle be disrupted or blown away by feedback processes. We don't have good observational constraints on how much mass is in Phoenix A's accretion disk at any given time, which adds another layer of uncertainty to our mass estimates and our understanding of the system's dynamics. There are also unresolved questions about the connection between Phoenix A and its host galaxy. We can identify which galaxy at the center of the Phoenix cluster houses Phoenix A, but we don't have detailed observations of that galaxy's structure, stellar population, or kinematics. Is it a normal giant elliptical galaxy, or does it have unusual properties that might provide clues about how it and Phoenix A co-evolved? What's the velocity dispersion of stars in the galaxy, and does it match the expected relationship with black hole mass? Are there signs of recent galaxy mergers that might have fed Phoenix A? The host galaxy holds important information about Phoenix A's history, but observing it in detail is challenging because it's so distant and because the bright emission from Phoenix A's active galactic nucleus can overwhelm the light from the galaxy's stars. Future observations with next-generation telescopes might be able to tease apart these components and give us a better picture of the host galaxy. But for now, we're working with limited information. The broader implications of Phoenix A for cosmology also remain somewhat uncertain. Does Phoenix A represent a typical outcome of black hole growth in massive galaxy clusters, or is it an outlier, a lucky combination of circumstances that allowed it to grow larger than most? As we survey more of the sky and find more ultramassive black holes, we're starting to build up statistics on their abundance and properties, but the sample is still small and the selection effects are significant. We're more likely to find actively feeding black holes like Phoenix A because they're bright and easy to detect, while dormant ultramassive black holes lurking in distant clusters might escape our notice. This means we might be getting a biased view of the ultramassive black hole population, overestimating how common extreme systems like Phoenix are. Or maybe Phoenix A is actually more typical than we think, and the universe contains many more such objects that we just haven't found yet. Resolving this requires larger surveys, covering more sky area and pushing to greater distances, work that's ongoing but still incomplete. There's also the question of whether studying Phoenix A can teach us anything about dark energy, the mysterious force causing the universe's expansion to accelerate. Dark energy dominates the universe's energy budget today, making up about 70% of the total, but we have almost no idea what it is or where it comes from. Some speculative theories link dark energy to the properties of spacetime near black holes, or to quantum vacuum energy, and a few even suggest that black holes themselves might be sources of dark energy. These ideas are highly controversial and far from mainstream, but they highlight how little we understand about the fundamental nature of spacetime and gravity. Phoenix A, with its extreme mass and gravitational field, might provide a testing ground for exotic theories about gravity and cosmology. But extracting meaningful tests from observations is incredibly difficult. The effects we're looking for are typically tiny, buried in noise, and overwhelmed by more mundane astrophysical processes, and teasing them out requires both exquisite observational precision and sophisticated theoretical modeling. As of now, Phoenix A hasn't revealed any obvious deviations from general relativity or any clear signs of new physics, but that doesn't mean they're not there, just that we haven't figured out how to see them yet. Finally, there's a meta question about what we don't know that we don't know, the unknown unknowns. Every major discovery in astronomy has revealed phenomena that nobody predicted, from the accelerating expansion of the universe to fast radio bursts to the unexpected abundance of exoplanets. Phoenix A might be harboring surprises that we can't even conceive of with our current frameworks, aspects of its behavior or properties that won't make sense until we develop new theories or new ways of observing. History suggests that when we push into extreme regimes, whether it's extremely high energies, extremely small scales, or extremely large masses, nature tends to surprise us. And Phoenix A represents one of the most extreme regimes accessible to observation. It's entirely possible that future observations will reveal something about Phoenix A that forces us to rethink fundamental aspects of physics, some anomaly or unexpected behavior that becomes a new puzzle driving the next generation of research. The fact that we can even ask these questions, that we can identify the boundaries of our knowledge and recognize what we don't understand, is itself a remarkable achievement, and Phoenix A stands as a monument to both how far we've come in understanding the universe and how far we still have to go. If we could fast forward through cosmic time and watch Phoenix A over the next trillion years, over the next 100 trillion years, over timescales so vast, they make the current age of the universe seem like the blink of an eye, what would we see? The future of Phoenix A is written in the laws of thermodynamics and quantum mechanics, a slow, inexorable march toward equilibrium that will play out over eons beyond human comprehension. And understanding that future gives us perspective on what Phoenix A truly is. Not just a momentary phenomenon, but a structure that will persist long after everything we know has turned to dust. Let's start with the relatively near future, the next few billion years. Right now, Phoenix A is in the prime of its life, actively feeding and growing, surrounded by a cluster full of gas and galaxies. But this won't last. The intense star formation in the Phoenix cluster will exhaust the available gas supply within a few 100 million years, converting it into stars or heating it to such high temperatures that it can't cool and collapse anymore. As the gas runs out, the fuel supply for Phoenix A will dwindle. The accretion rate will drop, the jets will weaken, and eventually the system will enter a quiescent phase where Phoenix A sits mostly dormant, no longer the blazing quasar-like object we observe today, but a sleeping giant. This transition from active to inactive has happened to countless black holes throughout cosmic history, including the one at the center of our own Milky Way. Sagittarius, a star, was probably much more active in the past when our galaxy was young and gas-rich. But today, it's relatively quiet, feeding on occasional wisps of gas from stellar winds or the rare star that wanders too close. Phoenix A will follow a similar trajectory, its age of peak activity fading into memory encoded only in the structure of its environment, those cavities in the cluster gas serving as fossils of past glory. But even in its dormant state, Phoenix A will continue to grow, just much more slowly. Galaxy mergers will still happen, albeit less frequently as the universe expands and systems become more isolated. Each time another galaxy falls into the Phoenix cluster and eventually merges with Phoenix A's host galaxy, there's a chance its central black hole will spiral in and merge with Phoenix A, adding to the mass. These merger events will become increasingly rare as cosmic expansion accelerates, driven by dark energy, and galaxies outside gravitationally bound clusters, like Phoenix, drift away from each other faster than they can collide. Within the Phoenix cluster itself, mergers might continue for tens of billions of years, but eventually even that will stop as the cluster settles into a final configuration, a single massive galaxy at the center, surrounded by a halo of dark matter, and whatever stellar remnants haven't been consumed. By the time the universe is 100 billion years old, roughly 7 times its current age, star formation across the cosmos will have essentially ceased because all the available gas will have been used up or expelled from galaxies by feedback processes. The last generation of stars will burn through their fuel and die, and no new ones will replace them. Phoenix A at this point might weigh slightly more than it does now, perhaps 150 billion solar masses, if it's been lucky with mergers, and it will sit at the center of a dead cluster, surrounded by cooling white dwarfs, neutron stars, and black holes, the remnants of all the stars that once blazed. The universe will enter what cosmologists call the degenerate era, a phase where the primary sources of light are no longer fusion-powered stars, but the feeble glow of brown dwarfs and the occasional white dwarf that hasn't quite cooled to background temperature yet. Phoenix A will be one of the most massive objects, still recognizable as a distinct structure, a point of gravitational focus in an otherwise darkening cosmos. As time marches on into the deep future, past 100 billion years, past 1 trillion years, the universe will continue to expand and cool. Galaxies outside gravitationally bound clusters will have receded beyond the cosmic horizon, their light redshifted so severely that they become undetectable. The observable universe from Phoenix A's perspective, if there were anyone there to observe, would shrink to just the remnants of the Phoenix cluster itself. Everything else would have been carried away by cosmic expansion into a region of space-time that can no longer communicate with Phoenix A. The cluster would be an island universe, isolated and alone, much as early 20th century astronomers once thought the Milky Way was the entire universe before they discovered the existence of other galaxies. Within this isolated island, things will continue to evolve, but in ways that are increasingly strange and slow. Stellar remnants will occasionally collide or have close encounters, merging to form slightly more massive objects, or being ejected from the cluster entirely by gravitational slingshot effects, over timescales of 10 to the 15 to 10 to the 20 years, which are numbers so large they're almost impossible to conceptualize. Most stellar remnants in the cluster will either fall into Phoenix A or be ejected into the void. This process is called gravitational relaxation or dynamical friction, and it's the cosmic equivalent of particles in a gas bouncing around until they either stick together or fly apart. Phoenix A's gravity will gradually sweep up most of the remaining mass in the cluster, growing incrementally with each capture, while a fraction of objects will gain enough energy from gravitational interactions to escape the cluster entirely, wandering off into the expanding space between cosmic structures. By 10 to the 20 years, Phoenix A might be essentially the only thing left in its region of space, a solitary black hole weighing perhaps a few 100 billion solar masses, surrounded by nothing but empty space-time, growing ever more empty as dark energy drives expansion. And at this point, something remarkable begins to happen, or rather continues to happen, but finally becomes noticeable. Phoenix A starts to evaporate. Stephen Hawking's discovery that black holes aren't truly black, but emit radiation due to quantum effects near the event horizon means that every black hole is slowly losing mass, converting its gravitational energy into thermal radiation and leaking that energy away into space. For stellar mass black holes, this process is incredibly slow, with evaporation timescales far exceeding the current age of the universe. But Phoenix A is so much more massive that its Hawking temperature is correspondingly lower, and its evaporation timescale is correspondingly longer. The temperature of Hawking radiation is inversely proportional to the black hole's mass. So a black hole as massive as Phoenix A has a temperature incredibly close to absolute zero, far colder than the cosmic microwave background that pervades space today. In the early universe, black holes actually gain mass from absorbing cosmic microwave background photons faster than they lose it through Hawking radiation, so they grow rather than shrink. But as the universe expands and cools, the cosmic microwave background temperature drops, and eventually it becomes cooler than even Phoenix A's Hawking temperature. At that point, which will happen sometime in the next few trillion years, Phoenix A will begin net evaporation, radiating away more energy than it absorbs. The rate of evaporation is incredibly slow at first, completely negligible compared to any other process, but it's inexorable, and it accelerates as the black hole loses mass. The lifetime of a black hole due to Hawking evaporation scales with the cube of its mass, which means small black holes evaporate much faster than large ones. For Phoenix A, the time scale is roughly 10 to the 100 years, a number written as 1 followed by 100 zeros. To put this in perspective, the age of the universe is only about 10 to the 10 years, 1 followed by 10 zeros. The ratio between these timescales is so vast that there's really no analogy that captures it. If the current age of the universe were 1 second, Phoenix A's evaporation timescale would be longer than the age of the universe by a factor of many billions. We're talking about a duration so long that quantum fluctuations might cause new universes to spontaneously tunnel into existence from the vacuum. Events that have probability effectively zero on any timescale we care about, but become possible if you wait long enough. During most of this evaporation period, Phoenix A will look essentially unchanged, sitting in empty space, imperceptibly losing mass through the emission of Hawking photons, so rare and low energy that detecting them would be impossible, even in principle for any realistic apparatus. The black hole will remain cold, dark, and seemingly eternal for timescales that dwarf the entire history of stars and galaxies by factors we can barely express. But eventually, after an almost incomprehensible wait, Phoenix A will have radiated away a significant fraction of its mass. As it shrinks, the evaporation accelerates because the Hawking temperature increases as mass decreases. A black hole that started with 100 billion solar masses will spend most of its evaporation time losing the first 90 billion solar masses. Then the rate speeds up and it loses the next 9 billion much faster, and so on. The final phase of evaporation happens in a rush by comparison, though still over timescales of billions or trillions of years. When Phoenix A is down to perhaps 1 million solar masses, it will be radiating at a noticeable rate, glowing with Hawking radiation across the electromagnetic spectrum. As it shrinks further, the temperature rises and the radiation becomes more intense and shifts to higher frequencies, from radio to infrared to visible light to ultraviolet to X-rays and eventually to gamma rays. When Phoenix A reaches a mass of about 1,000 solar masses, it will be shining as brightly as a star, a bizarre reversal of its earlier existence, when it was a dark consumer of light. And in the final moments, when the mass drops below 1 solar mass, and then below that of a planet and then a mountain, the evaporation becomes explosive. The final second of Phoenix A's existence will release more energy than all the stars in a galaxy, a brilliant flash of gamma rays and exotic particles marking the disappearance of what was once the most massive black hole in the universe, and then nothing. The mass and energy that was Phoenix A will have been completely converted into radiation and particles that disperse into the void, and the black hole will cease to exist. What remains after this final evaporation is uncertain and depends on physics we don't fully understand. Most calculations suggest the black hole evaporates completely, leaving nothing behind except the radiation it emitted. But some theories propose that a stable remnant might remain, a tiny object containing all the information about what fell into the black hole over its lifetime, preserved in some compact quantum state. These remnants, if they exist, would be incredibly tiny, far smaller than an atom, but they would persist indefinitely, scattered throughout the universe as fossils of the black hole era. Other theories suggest even more exotic endpoints. Perhaps the final evaporation creates a bridge to a baby universe that buds off from our own, inheriting some properties of the parent black hole. Or perhaps the information is radiated away in subtle correlations in the Hawking radiation that we don't yet know how to calculate. The final fate of Phoenix A touches on some of the deepest unresolved questions in theoretical physics, and we won't know the answer until we have a complete theory of quantum gravity. But regardless of the details, the broader picture is clear. Phoenix A, despite its immense mass and its dominant role in shaping galaxies and clusters, is not eternal. Given enough time, it will evaporate and disappear, returning its mass energy to the universe in the form of radiation. This fate awaits all black holes, from the smallest stellar remnants to the largest ultramassive monsters. In the unimaginably distant future, long after stars have ceased to shine and galaxies have dispersed or collapsed, the universe will enter what cosmologists call the black hole era, a phase where black holes are the dominant remaining structures. This era will last from roughly 10 to the 40 years to 10 to the 100 years after the Big Bang, an expanse of time that makes the entire age of stars and galaxies seem like a brief prologue. During the black hole era, the universe will be a cold, dark, nearly empty place, with black holes of various sizes drifting through space, slowly evaporating. The largest black holes like Phoenix A, or its descendants, will be the last to go, persisting long after smaller black holes have vanished. But eventually, even they will succumb to Hawking evaporation, and the black hole era will give way to what's called the dark era, a phase where the universe contains nothing but extremely dilute radiation, perhaps some stable particles like electrons and positrons, and possibly those exotic remnants we mentioned. The temperature of space will approach absolute zero, and nothing interesting will happen anymore, because there won't be enough free energy available to drive any processes. The universe will have reached a state of maximum entropy, the heat death that thermodynamics predicts for any closed system, a state of perfect equilibrium where no gradients exist, and therefore no work can be done. From that perspective, Phoenix A's eventual evaporation is not a tragedy, but a completion, a return of borrowed order to the universal tendency toward disorder. Black holes are localized regions of extremely high entropy. In fact, they have the highest entropy possible for any object of a given size, and when they evaporate, that entropy is released into the radiation field, spreading it even more thinly across space. The universe is running down, approaching thermal equilibrium, and the evaporation of black holes is a necessary step in that process. But before we get too depressed about the heat death of the universe, it's worth noting that these timescales are so absurdly long that they're essentially meaningless for anything we care about. The universe could go through countless cycles of complexity and simplicity within spans of time, far shorter than Phoenix A's evaporation time. Life, intelligence, and perhaps even new forms of structure we can't imagine might arise and flourish and fade many times over before the final black holes wink out. The deep future is largely unknowable because we don't understand the full laws of physics that will govern it, and there might be surprises awaiting that change the entire picture. Some speculative ideas in cosmology suggest the universe might not simply run down, but could undergo phase transitions or quantum tunneling events that restart structure formation, or that consciousness and computation could persist even in the dark era by exploiting the residual energy in black hole evaporation, or in the zero-point fluctuations of quantum fields. These ideas are highly speculative, bordering on philosophical rather than scientific, but they remind us that our current understanding is provisional and limited. What we can say with more confidence is that Phoenix A's role in the cosmic story has multiple chapters. In its youth, it was a seed that grew rapidly, assembled from the collapse of massive stars or gas clouds in the early universe. In its adulthood, which we're witnessing now, it's a dominant force shaping galaxies and clusters, feeding voraciously and sculpting its environment through powerful feedback. In its long middle age, lasting tens to hundreds of billions of years, it will be mostly dormant, a gravitational anchor for its cluster, occasionally feeding on merger debris, but otherwise quiet. And in its extreme old age, over timescales that make the entire age of stars seem like nothing, it will slowly evaporate, converting its mass back into radiation in an elegant reversal of the process that created it. Each phase tells us something different about the universe. The formation phase teaches us about the early universe and the emergence of structure. The active phase shows us the interplay between black holes and their environments, the feedback processes that regulate galaxy growth. The dormant phase illustrates the long-term evolution of cosmic structure and the effects of dark energy on gravitational binding. And the evaporation phase, though we'll never observe it, reveals the quantum nature of space-time and the ultimate limits of gravitational collapse. Phoenix A is not just an object. It's a process, a thread woven through the entire history of the universe, from near the beginning to beyond the end of stars. When we observe Phoenix A today, we're seeing just one moment in a story that spans the entire temporal extent of physical reality. And that perspective is humbling and awe-inspiring in equal measure. It reminds us that while we are brief and small, our ability to understand and contemplate these vast scales connects us to something much larger. Phoenix A will outlast our sun, our galaxy as a structured system, perhaps even the last stars in the universe. But it will not outlast the laws of physics themselves, and those laws predict its eventual dissolution. There's a poetry in that, a kind of cosmic justice, where even the most powerful objects in the universe must eventually yield to entropy and quantum mechanics. Nothing is truly permanent, not stars, not galaxies, not even black holes that weigh 100 billion times the mass of the sun. Everything that exists is temporary, persisting for a while, before transforming into something else. And the timescale of that persistence, whether it's the Mayfly's day or Phoenix A's 10 to the 100 years, is ultimately just a number, significant to those who experience it, but arbitrary from the universe's perspective. What matters is not how long things last, but what they do while they exist. And Phoenix A has done something remarkable. It has shaped the evolution of galaxies, triggered the formation of billions of stars, carved structure into space on the largest scales, and served as a laboratory for the most extreme physics accessible to observation. It has pushed our understanding to its limits and beyond, forcing us to confront gaps in our knowledge and inspiring new theories and observations. And it has captured our imagination, this invisible monster lurking at the heart of the Phoenix cluster, simultaneously destroying and creating, the ultimate expression of gravity's power and the ultimate reminder of nature's capacity for extremes. Long after humanity is gone, if we don't find a way to persist beyond our biological limitations, Phoenix A will still be there, sitting in the dark, slowly leaking Hawking photons into an expanding and cooling universe, a monument to an era when galaxies blazed and black holes grew fat on gas and starlight, waiting patiently for the eons to pass and its final transformation to arrive. And in that patience, there is a kind of grace, an acceptance of what must be, that even a black hole, the most voracious object in existence, must eventually give back what it has taken, must return to the universe, the energy it has held in gravitational bonds for longer than thought seems possible, must complete the cycle that began with collapse and ends with radiation, bringing the story full circle and reminding us that in the deepest sense, nothing is ever truly lost, only transformed, only redistributed, only changed from one form of energy to another as the universe continues its long march toward equilibrium, toward silence, toward that final state where even the memory of Phoenix A will exist only as a slight excess of entropy in the thermal radiation, filling infinite space, a whisper that once long ago in a cluster far away, there was a black hole so massive it seemed eternal, and for a time measured in numbers beyond counting, it almost was.